So for this project, me and my co-authors, Mike Oskin and Alba Padilla, used post-earthquake Lidar to remotely map the surface ruptures for the 2019 Ridgecrest Earthquake sequence. And the goal of this project was to create these rupture maps that we could then use to assess the reproducibility of rupture mapping from exclusively a Lidar data set, and then also test the accuracy of those maps against rupture maps that were produced using a variety of remote data sets as well as field observations. And so to do this, each of us independently produced a rupture map using just the earthquake Lidar. And then those rupture maps were converted into rasters. And then we use those rasters and the number of pixels in those rasters to assess overlap between the maps. And so at the bottom left of the poster in the yellow panel, there's a figure and some bullet points that are explaining that process of rasterization and why we do it, especially where we add buffers to the rasters just to account for differences in line placement. And then we look at the overlap between somebody's rasterized map and somebody else's buffered map, and then the number of shared pixels over the person's mapping gets us the percentage. And so then in the middle of the map is the 5 rupture maps that we compare against. So the 3 across the top are by each of the authors. And then the 2 at the bottom are the 2 published rupture maps by Duras et al. And Ponti et al. From 2020. So they were put out last year. And both of those maps use a variety of different sources for their lines. So things like drone imagery or image differencing, field observations, etc. And just looking at the maps, you can see some variability. So sort of at this larger scale. So mapper 1, for example, has quite a few lines at the northern and southern end of the northwest southeast trending rupture from the 7.1, whereas mapper 2 does not have very many lines at that northern and southern end. And so that's a good example of some of these, where some of these differences in percent overlap are coming from. And then you can also see, if you compare our 3 maps to the published maps, there are places where we have gaps. So we just don't have, we can't connect lines or something like that. We're just missing lines. And that's usually because the rupture there is really hard to see in the Lidar. So it either has very little vertical displacement or it's just so small that it doesn't show up, but it was visible in the field or with a different data set. And so the table on the right-hand side is showing the percent overlap between mappers. So comparing somebody's rasterized map against somebody else's map with a buffer, either 1 meter, 2 meter, or 5 meter buffers. And again, those buffers are just to see sort of how much room for error we can allow in line placement and how that changes the amount of overlap that we see. And it does increase it. It does get us to have a little bit more overlap or slightly higher percent of shared pixels. But it doesn't really get us to the point where it's like, yes, okay, these maps are exactly the same. And so what this shows is that these differences in the maps really are coming more from differences in how the Lidar was interpreted or differences in what was mappable with the information available. So Lidar only or other data sets as well. And then really sort of our take home point from this all is that the post-earthquake Lidar alone is not really enough to fully capture everything from a surface rupture from an event with mostly horizontal or very little vertical displacement. And then just at the bottom is a comparison looking at our mapping versus mapping done by one of the authors from the drone imagery. So you can just see how much more detail is captured there. Yeah, so that's the explanation of what we've done so far. If you want to know more or have any questions, feel free to reach out to me. My contact information is on the poster, and I look forward to talking to you. Thank you.